1.2 System Notations. Block diagram. First of all, what are they? They are a simplified representation of a system. They represent the relationships between functional system sections or blocks. And I think we have a, here is a picture of a block diagram. Let's talk about it a little more. First of all, lines or arrows indicate flow of information or control signals. So if we look at this, we'll see we have, lines and we have arrows, and these are indicative of the flow of information. Next item here we're mentioning is a bus. And a bus is a group of wires that serve as data or address elements in a computer system. So let's take a look at here in our graph, or in our picture here, we have a number of buses indicated. The blue here, this is indicating a bus. Here we have another bus over here. We have similar buses over here. You'll note that the buses, some of the buses have numbers attached to them. Notice this one 32, this one 64, this one 8. These are all what we would call parallel buses because they're moving, in this case there's 64 wires here. And just as one example, from system memory to the microprocessor, there is actually 64 physical connections, so we can move 64 bits of data at a time. We'll pick this up later in the book, but 64 bits is equivalent to 8 bytes. So 8 bytes of data can be moved to the processor at one time because there is a 64-bit data bus here. In the same manner, here we have a 32-bit bus, and this is moving data between video memory and the video display. Down here we have an 8-bit bus that's moving data between the I/O controller and the printer. We also have some buses. Notice these are indicated with just the number 1, and in this case the number one wire in a bus would be indicative of a serial bus vice a parallel bus. And let's see, then we also have, here we are, control lines. These are bold single arrows pointing from the controlling block to the controlled block. So we have a controlling block and a controlled block. And so in this particular diagram, you will see notice the large black lines here. There's one over here, another one here. And what these are indicating is, in this case, for example, the microprocessor is controlling the video controller. The microprocessor also is controlling this thing we call the bus. The I/O controller is controlling the mouse, keyboard, and printer. And here we also have the microprocessor controlling the communications controller. In this case, it would be a modem, network interface cards, etc. The block diagram. Now remember, this is not a class on computers. This is a class. What we're looking at here is simply a block diagram, and a block diagram is useful in understanding the general nature of a system. It provides the big picture without the detail. And you notice the detail, for example, a detailed picture would have shown you those 64 lines instead of just showing you that bus that contains 64 wires. A schematic diagram would have actually shown you the 64 wires. A block diagram is also helpful to gain an understanding and also to troubleshoot. Oftentimes, if you're troubleshooting a system, a block diagram can help you to isolate the general area where a problem could be. Then we have flowcharts. A flowchart is another way to describe the behavior of a system. Flowcharts are useful for a number of things, for programming computers, troubleshooting complex systems, describing the operation of a system, explaining systems to users, and optimizing the design of a system. Now here we have in your text, this is in your textbook, these are, here we have some pictures of some flowchart symbols, and we'll give a little bit of definition of their meaning. And then here is an actual flowchart, a simplified flowchart for troubleshooting a computer system. As a rule, and I note down here at the bottom, as a rule, block diagrams are connected or concerned with electrical functions of a system. Okay, block diagrams concerned with electrical functions of a system. This is what we looked at on the previous slide. Whereas flowcharts, okay, flowcharts, which this is, are used to describe the behavior of a system. Now, I'll just describe a couple of these. Notice here we have this rectangular box. It indicates a process used to present a process or a complete operation. Notice here, one example here is to turn on power. This would represent a complete process or operation. Then notice here's another one. The diamond here, it represents a decision. It's used to represent a branch to one of two paths based upon the indicated decision. So here we have, here's another example of this, or a example of this. The diamond is used, power indicator on. Now in this case it would probably be maybe an LED light or something that indicates power is on, and there's simply a decision. Is there power, is there not power? If there is power, you can continue down this stream. If there is no power, then you go over here. You know, is it plugged in? Is it turned on, etc. The oval shape here is a terminator used as an exit point for a flowchart. Notice that would be down here. This would be our exit point. And the off-page connector here, this is used to indicate something, in this case, used to indicate a connection to a similarly labeled symbol on another page of a multi-page flowchart, because often in electronic systems these flowcharts become just monumental in size, and you may have multiple pages to depict a flowchart. Then graphical data. Graphical data. A graph is used to communicate technical details about the behavior of an electronic system. Many types of graphs are available. We're going to look at three of them. We're going to look at linear, logarithmic, and polar graphs. Graphs with equally spaced divisions representing the scales are called, and we refer to these as line graphs, or in this case a linear scale. When values on a graph fall between divisions on a scale, an estimate is made of the value. This is called interpolation. Now, on the next page here, we have a picture of what we call a line graph or a linear graph. And the reason it is a linear graph is because both, notice here, horizontal and vertical lines have equally spaced divisions. Okay, you'll notice here the horizontal, you'll notice there's between 555, 50 to 600, 600 to 650, 650 to 700. There was equal spacing going horizontally, and hence also going vertically there is equal spacing, and hence the term a linear graph. That word we had talked about earlier on the previous slide, interpolation, it's when values fall in between numbers on a given scale, you must estimate. And so say we want to know what is the value that exists at maybe this point right here, and we would need to make an estimation based on You have to make the estimate based on the values that are in between, in this case, between here and between here. Here we have a logarithmic graph. Now, a logarithmic graph it differs from a linear graph in that there is non-uniform spacing. In this case, and when I say non-uniform, we have an example. In this case, 2 is not midway between 1 and 3. And so if you look at this graph, there's some interesting things about it. You'll note it is used to depict a very wide range of frequencies. In this case, it goes from 1 here all the way up to 1,000, and this is in megahertz. So from 1 megahertz to 1,000 megahertz. So it's graphing a very wide field of data. Now you'll notice here from 1, here we would step to 2, and then to 3. And you'll notice that 2, usually you would expect 2 to be midway in between 1 and 3, but in a logarithmic graph, this simply isn't the case. And you'll notice you go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we get to 10. And then starting at 10, we're going to make jumps of not 1, but of 10. So in this case, it goes 20, 30, 40, 50, 60, 70, 80, 90, and then 100. And then from here, it makes jumps of 100, 200, 300, etc. So this is an example of what we refer to as a logarithmic graph. It is not mentioned in your text, but this graph depicts what we call a low-pass filter. And it passes, in this case, it's between about here and here. It's passing, well, you're getting a much larger signal. This would be from about 1 to roughly 20 megahertz. And then from here to here is where it is what we call rolling off, between about 20 to 40 megahertz. And then from 100 megahertz on, it is severely attenuated. And attenuated means it's severely diminished in size. Then we have the polar graph, kind of like the polar bear. No, I'm kidding. All right, polar graph. This graph is of the brightness of a light-emitting diode. Okay, a light-emitting diode is often referred to as an LED. And this is the graph is of the brightness of a diode as it is viewed from different angles. Okay, so here you've got, this is the angular view, and this is the LED, and what you're graphing here is how much of the potential brightness of that LED, how much of it can I see from different viewing angles. And I might mention here, an LED is a device that emits light when electrical current passes through it. In this case, each of the concentric circles represents an intensity of light as viewed from 0 to 90 degrees. Each radial extending from this center outward corresponds to the viewing angle. And so as you can see here, if you're at 40 degrees, let's see, what are we going to get? We're going to see about 40% of the brightness of this LED. If we were at 10 degrees off from it, we would see, in this case, 100% of its brightness. The interpretation of the data from a polar graph is the same as in the previous two graphs. The viewing angles separates the polar graph from the linear and the logarithmic. And here again we have a line graph. This particular graph is very similar to the first one we look at. It is a linear graph. The difference, let's see, this graph of the PhET characteristics is similar to the first graph, except that it depicts a family of curves rather than just one. The first linear graph had just one single value graph. Here we have a variety of of different values graphed on this linear graph. And the FET, we will talk about FETs later in this course. It is referred to as a field effect transistor. Okay, wiring diagrams. Wiring diagrams frequently used in electronics. They are a pictorial sketch that represents the components in a circuit. Each component is labeled for clarity. The lines in the diagram represent the wires providing the electrical interconnections. And we have an example here. Here is a basic wiring diagram. And again, the purpose is not to teach this system, but rather just to introduce the concept of a wiring diagram. In this particular picture here, we have a three-phase motor. Over here we have the switches that will turn this motor on or off. We have a couple of different operators here that can power this motor. We're not told what this motor does, but it's simply that it's a three-phase motor. We see here we have the power source, and this is three-phase AC. Phases A, B, and C are depicted here. This is used in usually in industrial settings. We see something here labeled K, and the K's here are all tied together. These typically are indicating a relay. In this case, these relays would apply power to this particular motor. And then we have some thermal switches here. Thermal switches act as fuses. If there is too much current being pulled by any of these phases, the relay or the thermal switches would open, shutting the system off. And then we have a 120 volt AC power source over here. Again, another, in this case, a fuse if the system overloads. So anyway, this is a depiction of a wiring diagram. Then we have schematic diagrams. And schematic diagrams are a graphical representation based on symbols that show how all electronic components in a system are connected. And probably the key word here is all electronic components. Schematic diagrams are one of the most important ways of communicating technical information about a circuit's, notice this, normal behavior. Some common electrical symbols used in schematics are shown below on the following slide. And so here we see some common electronic components. Now, we're not going to go into these at this time. Throughout this course, we will probably look at every one of these. And then here we have a schematic of an electronic circuit. This actually comes from your simulation software that you'll be using. In this particular case, we see a number of devices depicted. Here we have an op-amp. In this case, it's a 741 op-amp. We see a resistor. Here is a 1 k-ohm resistor. Here is another resistor. Here is a capacitor. Over here we show a signal source. In this case, the signal source is the square wave at 5 volts coming in at 10 kHz. Here we see a ground. Down here we see a positive voltage. Here we see a negative voltage. This particular circuit is a integrator. It is is a circuit that develops a ramp. It looks kind of like this, the output of this device. But right now this is not of importance, but this just is an example of an electronic circuit.